A skateboard rolls down, sweeps through the bottom, and climbs the opposite wall. Then comes the strange instant. High on the far wall, the wheels nearly stop. The board has no backward speed yet. Watch what happens next. Follow the nose for the next instant. Instead of waiting at the wall, it tips back toward the bottom and gathers speed. So zero speed did not mean nothing was changing. What reached into the instant and sent it home? To isolate that question, make one model. Treat board and rider as one point, P, constrained to a rigid circular track. Ignore wheel rotation, pumping, air drag, and losses. Assume contact is maintained. The silhouette stays while its calculation copy becomes P. Mark the circle's center O and lowest point B. At time t in seconds, call the distance from O to PR of t, measured in meters. That distance is our first coordinate, made visible by the amber arm. As P travels, the arm turns but never stretches. The rigid circle fixes R of t at radius r, also in meters. The radial coordinate does not describe the ride. It records the constraint the ride cannot escape. Constant distance means radial speed and radial acceleration are both zero. Physics writes time derivatives with dots. One dot means one derivative, two dots mean two. Therefore r dot equals 0 and r double dot equals 0. The motion needs a second coordinate. Measure the signed angle from the downward line through B to the radius arm. Call it phi of t. Phi is 0 at B, positive right, negative left, and measured in radians. Bolt a tiny compass to P. Its cyan direction, r hat, points outward from O through P, the opposite is inward. This arrow rotates with location at every track position, so radial never means simply up, down, left, or right. The mint direction, phi hat, lies along the track and points toward increasing phi. It rotates with P, even when motion reverses. A coordinate direction does not promise where the board moves. It is the local direction we call positive. Here is why a fixed radius does not mean zero acceleration. Freeze P for an instant and extend its velocity straight ahead. Without the track, that tangent ghost would continue. The real board instead bends away from the ghost and remains on the circle. The needed bend points inward, opposite positive r hat. Call its signed radial component a sub-r. If phi dot is angular velocity, then the circular path rule is a sub-r equals minus r phi dot squared. Faster motion demands more inward bending. Speed can also change along the track. Call that component a sub-phi. Two dots on phi mean angular acceleration, and fixed radius makes a sub-phi equal r phi double dot. At a wall, phi dot can be 0, while phi double dot is not. Now reveal the forces in our ideal model. Gravity gives the board rider point a weight vector W, straight downward. Its magnitude is mg. M is mass in kilograms, and g is gravitational acceleration, 9.8 meters per second squared near Earth. The track supplies the other force, the normal force. Write N for its magnitude in newtons. Its ivory arrow points inward, perpendicular to the surface. In this frictionless point model, there is no third push along the track and no separate centripetal force arrow. Centripetal names a job, net force bending motion inward. Normal can do it, and radial gravity can share it. But because normal is perpendicular to the track, it cannot speed the board or reverse it in this ideal, lossless model. Start with the inward bending job. Project downward weight onto positive r hat. The right triangle gives an outward radial component mg cosine phi. At the bottom, phi is 0 and weight points outward, opposite normal. Use the signed radial direction exactly as drawn. Outward gravity contributes plus mg cosine phi. Inward normal contributes minus n. Newton's second law says their sum equals mass times inward radial acceleration, minus mr phi dot squared. The radial ledger reads mg cosine phi minus n equals minus mr phi dot squared. Each sign has a picture. Outward is positive, while normal and acceleration point inward. The equation determines how large contact must be. At the bottom, speed is greatest, so inward bending is large and n exceeds outward weight. At a turning point, speed is 0, so radial acceleration vanishes. Yet the board turns around. The radial job is not our answer. Return to weight and look along phi hat. Its projection has size mg sine phi, but on the right it opposes positive phi. The sine component is minus mg sine phi, pointing down the track toward B. Read the sign. On the right, phi and sine phi are positive. The leading minus makes the component negative. Its arrow opposes phi hat and points toward smaller angle, where the board begins returning. On the left, phi and sine phi are negative. The minus makes the component positive, along phi hat, again toward B. One formula changes sign because restoring direction changes side. At B, phi is 0, so this component vanishes. Elsewhere it supplies the speed-changing force normal cannot. Place it beside a sub-phi equals r phi double dot. Newton's second law connects cause to acceleration. Gravity points down, the track decides what changes the board's speed. Resolve gravity into local directions. Its outward radial piece opposes the inward normal force in the contact balance. Gravity along the track is minus mg sine phi, pointing home. Match that to mass times r phi double dot. Mass cancels. Divide by r. The model's exact law emerges. Now read the law as a motion story. On the right, phi is positive, so sine phi is positive and phi double dot is negative. Acceleration points toward decreasing angle. Even at the turning point, that non-zero angular acceleration starts the return. At B, phi and sine phi are 0, so a long track acceleration vanishes. But the board moves fastest there, making inward radial acceleration and normal force large. 0 along track acceleration differs from 0 total acceleration. On the left, phi is negative. Sine phi is negative, the leading minus makes phi double dot positive, and acceleration again points toward B. Right, bottom, left. The exact law changes sine in precisely the way a restoring law should. One detail prevents us from calling this simple harmonic motion yet. The exact law contains sine phi, not phi itself. That sign makes restoring strength nonlinear. The circular model is exact here, but a cosine clock has not been earned. Magnify a narrow window around B. Because phi is measured in radians, arc length on a unit circle is phi itself, while its projection is sine phi. Near 0, those two lengths nearly coincide. Farther away, their separation grows. Shrink release angle and watch the gap close. For small absolute phi in radians, sine phi is approximately phi. Substitute that into the retained exact line. The small angle law becomes phi double dot approximately minus g over r times phi. Acceleration is now proportional to displacement with opposite sign. Move right, accelerate left, move left, accelerate right. This spring-like line is approximate. Larger angles obey the exact sine law, not this simple proportional rule. To predict one ride, define the starting instant. Let t equal 0 when the board is released. Call it signed release angle phi 0, so phi at 0 equals phi 0. Release from rest means phi dot at 0 equals 0. Compare the small angle law with the oscillator pattern. Acceleration equals minus angular frequency squared times displacement. That squared factor is g over r. Define angular frequency omega 0 as the square root of g over r, measured in radians per second. Those conditions select a cosine. For small release from rest, phi of t is approximately phi 0 cosine of omega 0 t. At t equals 0, cosine is 1, so the board begins at phi 0 with a flat slope. Open a recorder beside the pipe. Its horizontal axis is time t in seconds. Its vertical axis is the same signed angle phi in radians. As the board moves, one shared state moves angle arc, cursor, and trace together. Nothing is independently animated. Follow one cycle. After 1/4 period, the board crosses B. After half a period, it reaches the opposite turning point. At 3/4 it crosses B again, and after one full period t, it returns to its starting angle and direction. One cosine cycle lasts 2 pi over omega 0. Substitute the frequency. Period t is approximately 2 pi times the square root of r over g. Mass is absent. A wider radius slows the ride, stronger gravity speeds it. Fold the recorder away and return to the wall. What sends the board home is neither centripetal force nor normal force. It is gravity's component along the track, minus mg sine phi, reversing with the side. The exact circular model uses sine phi and explains return while contact holds. Near B, small angles in radians let sine phi become approximately phi. Only then does motion become an approximate cosine clock with this period. The half-pipe is more than a curved ramp. Radius chooses coordinates, local directions separate contact from return, and gravity writes oscillation. Make R larger and the clock slows. Keep it small and the board traces our prediction home.